Hello, everyone. Okay, yeah, I'm on stage now. It's 5:30, so we're going to get started soon. I'm really excited about this session. If you know me, you know that I have been thinking about nutrients for basically my whole career, so 15 years or so now. And we have really great speakers, people that I know well and or work with. We're going to start off high level, looking at some materials flow analysis at a sort of national scale. We're going to do phosphorus and then nitrogen, and then move through some more detailed, I would say, studies that kind of get into some details about quantifying environmental impacts of beef and recovering nutrients in a dairy farm or in farm settings from manure, right? So if you study nutrients, you immediately get into agricultural questions, and then there's always manure to think about. So I'm looking forward to this. And our first speaker is Mikaela Algren, who I've been working with for, I guess, almost 4 years now. She's a graduate student at Colorado School of Mines and will be defending her PhD in a month, I think, pretty soon. It's kind of exciting. Studying anthropogenic nitrogen and phosphorus impacts. She earned a bachelor's degree in physics with a minor in environmental studies from Gustavus Adolphus College in 2017. With her current and future work, she hopes to aid progress towards a sustainable future for all of Earth's inhabitants. So I will hand it over to Mikaela, and I'm really looking forward to hearing your talk.
Hi, thanks, Chris. Okay. Start. Are we all good?
Looks good. Yep, I can hear you and
all right,
see your
awesome.
slides.
Okay, cool. So yeah, as Chris said, I'm Mikaela Algren. I'm a PhD candidate at Colorado School of Mines. And I'm going to talk today about assessing the potential of phosphorus loss mitigation strategies to eliminate both net anthropogenic phosphorus inputs and mineral or mined phosphorus demand in the United States. And we sort of find that these are these two things that we're trying to eliminate, net anthropogenic phosphorus inputs and mined phosphorus demand, turn out to be pretty similar metrics or baselines to look at. But anyway, yeah, this work is funded by USDA NIFA grant, and our team is a collaboration between Colorado School of Mines and Penn State. So why would we want to eliminate net anthropogenic phosphorus inputs and mined phosphorus demand? Well, if you're in the nutrient session and you study nutrients, you probably already know that that phosphorus loading in watersheds can lead to eutrophication and algal blooms in water bodies and anoxia and hypoxia in the worst case scenarios. But unlike nitrogen, we have a phosphorus scarcity problem additionally. And so even models that use high estimates of phosphorus reserves, and that's the crux of it, we don't really know how much phosphorus is available, predict global peak phosphorus production will occur around 2100, and that more than half of global phosphorus production will be supplied by Morocco in 2050. And so Morocco currently controls about 75% of known phosphorus reserves. And so this is definitely going to affect the United States because with current mineral phosphorus extraction rates in the US, our supplies are within 40 years of depletion. So we have these two metrics that we're using to evaluate mitigation strategies and put them into context. And this first one is net anthropogenic phosphorus inputs. And NAPI has been used to estimate phosphorus loading in watersheds, and it's the sum of fertilizer phosphorus input to crop production, animal diet supplement phosphorus, detergent phosphorus used in households, and phosphorus in food and feed imports, net food and feed imports. And so the fertilizer phosphorus is that red portion of the stacked bar that you see on the right. And the animal diet supplement phosphorus is the blue, detergent is the orange. The brown and yellow, which are really small slivers, are also fertilizer but not used for food crop production. And then the purple, net food and feed imports, is negative because in the US we actually have a net export of phosphorus and crop products. And so what we're actually trying to do with these mitigation strategies is reduce the net anthropogenic phosphorus inputs, not just these positive inputs up top. So the other metric that we're looking at is mined phosphorus demand. And we calculate US mined phosphorus demand using USGS phosphate rock statistics data. And essentially, it's the sum of the mined phosphorus needed to produce phosphorus fertilizer applied to soils, phosphorus supplements fed to animals, and elemental phosphorus used in industry, which is primarily used for detergents and pesticides. And so how is this different from NAPI? Well, it includes production waste. So in fertilizer production, phosphogypsum is produced as a waste product and it's landfilled. And it also includes the phosphorus used to produce exported crops. And so we end up with 25 billion kilograms of phosphorus in US mined phosphorus demand, and we had 1.7 billion kilograms of phosphorus in NAPI. Okay, so the phosphorus loss mitigation strategies that we're trying to put into context. The first one is variable rate technology, and variable rate technology encompasses anything that enables farmers to collect data at the subfield scale, like every 2 acres, for instance. And so going forward, I'm going to refer specifically to variable rate fertilization, and some studies on variable rate fertilization efficiency in reducing fertilizer inputs exist, but we've only been able to find one with regard to phosphorus. And this was for a study of corn-soy rotations in Illinois, and they found that fertilizer phosphorus inputs could be reduced by 12 to 41%. And there's a large margin for improvement in implementing variable rate fertilization in the United States because it's practiced on less than 20% of US cropland currently. Okay, the next management strategy is efficient manure utilization. And efficient manure utilization means that we're not applying manure phosphorus in excess, and we're also maximizing replacement of synthetic fertilizer. And the current situation for manure utilization is that most manure is currently applied on the farm where it is produced. So as animal production operations get larger and the number of operations decreases, transportation of manure to other farms becomes more important in order to use manure efficiently. The next phosphorus loss mitigation strategy is utilization of phosphorus recovered from wastewater treatment. In the current situation, most phosphorus in wastewater treatment is removed in primary treatment as sludge, is incinerated, and then landfilled. The issue with using phosphorus from wastewater treatment currently on agricultural land is that it typically has heavy metals and harmful organics included with the nutrients, and so it's not a very desirable fertilizer product. But we do have some emerging technologies in this space that enable high phosphorus removal from wastewater treatment, like 60 to 90%, through sewage sludge ash production. And one of the other cool things about this is that the fertilizer-ready product that's produced doesn't have heavy metals and harmful organics, and is also comparable in cost to phosphate rock. Okay, so the last phosphorus loss mitigation strategy that we're going to look at is elimination of avoidable food loss. So this is not taking food loss and recycling the nutrients through composting. We're talking about here reducing the amount of food that we waste and removing that amount of food from production and all of the embodied phosphorus related to that food's production. So the potential margin for improvement with this could be large. About 40% of all food produced is lost, and about 75% of this is avoidable. Okay, so now let's get into the results. This first graph shows the potential NAPI reductions with management strategies. So we're looking at net anthropogenic phosphorus inputs, and the bar at the far left is the baseline 2017 net anthropogenic phosphorus inputs that you saw from one of those first slides. And all of the following stacked bars show the reduced NAPI in blue, and the colored patterned bar represents the management strategy that is used to create that reduction. So in the first scenario, variable rate fertilization 1, we are modeling implementation of variable rate fertilization for all modeled crops in the SNAPNI model. And then for VRF2, we model VRF implementation for just the area used to produce corn. For manure 1, we are modeling national level efficient manure utilization. So that means there's no transportation limit on where manure can go to satisfy crop needs. And then manure 2 is county level efficient manure utilization. And that means that manure can only be transported within the county that it's produced in to meet crop needs. And then we do the same thing for wastewater treatment 1 and wastewater treatment 2. We have a national level efficient utilization and a county level efficient utilization. And then the food loss bars next. And so that's for elimination of all avoidable food loss and the embodied phosphorus that would have been needed to produce that. And so then we have 2 combination scenarios to show what the potential of these things are if we were to implement them in conjunction with one another. And the really optimistic scenario is combination 1, and that's variable rate fertilization of all modeled crops plus national level efficient manure utilization plus wastewater treatment recovery with national level utilization. And then a more realistic combination strategy is variable rate fertilization for all modeled crops, and then county level efficient manure utilization and wastewater recovery at the county level, or utilization at the county level. And combination 2 is interesting because implementing VRF reduces total fertilizer demand. And so there's even less manure that we can utilize at the county level, and then even less wastewater treatment recovered phosphorus that we can utilize at the county level as well, just because fertilizer demand is reduced. But even with that strategy, we can still reduce over 50% of NAPI, which is cool. So the potential mine phosphorus demand reductions are a little bit less interesting than I expected them to be, but it makes sense considering that the way that we calculate NAPI and the way that we calculate mined phosphorus demand is very similar. The main difference is that we're including phosphorus used to produce exported crops for this mined phosphorus demand scenario. So all of these management strategy reductions of mined phosphorus demand scale with the reductions that we saw in the NAPI graph above. Okay, so in summary, manure utilization and VRF have the greatest potential for moving the US toward phosphorus circularity, but food loss avoidance and wastewater treatment recovery closely follow VRF and will be really important pieces of the puzzle as well. And they're definitely within the uncertainty range of VRF, so let's not count them out. And interestingly, NAPI could be reduced by over 50% with widespread adoption of VRF and, at the very least, county level efficient manure and wastewater treatment phosphorus utilization. And I think that So there are obviously barriers to implementing, especially VRF and efficient manure utilization because of the cost of implementing VRF for farmers and the cost of transporting manure. But considering that there are externalized costs of phosphorus loss to the environment, I think we really need to think about how we can financially support farmers, VRT implementation, and efficient manure utilization efforts going forward. Okay, if you have any questions, you can contact me at malgren@mines.edu. That's it.
Okay, any quick questions for Mikaela? I forgot to mention that I had instructed the panelists, and so audience, you wouldn't know this. I've asked people to talk for about 10 minutes and have maybe just one question between, and then have more of a discussion at the end. I'll ask you just one question. What do you think is the biggest barrier to successfully utilizing manure more efficiently?
Transportation cost.
Yeah.
Yeah, absolutely. Yeah.
Yeah. It's a big challenge and sort of embedded in the way the livestock agricultural system is set up. So it's tough to figure out. But yeah.
Yeah.
Okay, well, let us have our next presentation, but please, if you have questions about phosphorus or Mikaela's presentation that you want to share, please do. I see something in the chat and I was going to try to look at it, but the chat is a little bit messed up. Okay, so I'll ask this question since we have a moment. Could you remind us how the non-ag fertilizer was calculated and what it includes? And also, have you looked at this data geospatially?
So,
nutrient expert. Yeah.
Yes. So the non-ag fertilizer supposedly includes like domestic fertilizer uses. Sorry, can you still see this window? Yeah, so it's a small sliver, and that data comes from USGS fertilizer sales data, and yeah, I'm not sure how they classify some fertilizer sales as non-ag and some as ag, but it must be the places where people buy it. But and then the other question was, have we looked at this data geospatially? So I did use the county level breakdowns of the manure and fertilizer demand and VRT effectiveness in order to calculate this, but I haven't made a map, and that's one of the next to-dos for this research for sure. It would be great to see like what the breakdown of each strategy at the county level is for sure.
Yeah, it's a big trade-off figuring all this, the data's at a county scale and trying to use that, but yes, it's also a field scale kind of issue. So, we're always wrestling with that spatial issue. Okay, our next speaker is Zia Chowdhury. He's a PhD student at Penn State in agricultural and biological engineering. He's in the chair of his committee. He has an emphasis, his research is on nutrient flows at the national and multi-regional level. Zia received his master's in environmental engineering and a bachelor's in leather engineering from Bangladesh University of Engineering Technology. And today he's going to be talking about an effort to take the nitrogen and phosphorus data from this nanny nappy place and put it into an IO model to help think about embodied nutrients in manufactured foods. And take it away, Zia.
Well, thank you, Dr. Chris, for those good words and introduction. I'm trying to share my screen.
Sure. Hope it works out.
Do you see? Everyone can see my screen?
Yep, it's not in the full presentation view, but yeah, we can see your screen. Yeah.
Okay. Well. So as Dr. Chris said, she's my advisor, and basically I'm a grad student from Penn State, and today I'll be presenting on like quantifying the nitrogen and phosphorus flows, or in short, like NMP flows embodied in the manufactured foods and NMP footprints in the United States. So I guess like many of our participants here in this session are familiar with the impacts from nutrients, but I'll reiterate some of the facts specifically focusing on US. So nutrient impacts both ecosystem and human health by driving eutrophication, biodiversity loss, and climate change. And USCP warned that the impacts of NMP could become one of the most expensive and challenging environmental issues in the US. However, the big issue is basically keeping the food system within the same safe planetary boundaries. So a study by Rockstrom et al. Demonstrated that both NMP cycles are hugely disrupted and beyond the safe operating limits of the Earth system. And US is basically one of the major hotspot for transgressing NMP planetary boundaries. So where we can see it clearly for the nitrogen and phosphorus. So estimates of embodied nutrients at the national scale or system level has implications in achieving several goals. And just adding to the discussion that we had, like for the very first keynote presentations on linking LCA to planetary boundaries, they sort of illustrated like the overall system experiences a higher trend of impacts. Even the per unit impacts are basically declining. So this sort of signifies the system level estimations. Here also we also interested in NMP footprints, and one of the major attributes of the footprints tool is engaging the consumer actively in the decision-making process. So this is basically the range of consumers and NMP footprints for the year 2012. And we'll see if our estimates sort of resemble or fall within this range. However, when it comes to like estimating the embodied nutrients at the national level, so it basically limited to the community level. However, Singh and our colleague mapped the nitrogen cycles into 2002 Bureau of Economic Input-Output Life Cycle Analysis, and also they calculated the nitrogen footprint using the same set of data. But here in our analysis, we'll map both NMP and basically focusing on the food specifically and avoiding like the nutrient use, specifically nitrogen in explosives, nitrogen in synthetics, and also phosphorus in detergent. So that's sort of like we are streamlining our approaches.
Hey, Zia, I'm so sorry to interrupt you. We're only seeing the first slide, and it's still in the PowerPoint window. So try hitting the presenter button down there. We're still on your title slide.
Oh my God, sorry about that.
Okay. Can you hit the...
So should I just stop sharing and start sharing again?
Well, have you hit the little, the normal presentation, the presenter button down there, and it's not working?
Yeah, it's just working on my side, but I'm not sure why it's not working on the other side.
Or do you have more than one screen, or?
No, I have like one screen, so I'm gonna share it again. So we had this. So
and you hit, it's strange that hitting present is not working. So
and like so should I start again, or like keep continue where I left?
Well, we need to be able to see your slides. So
yeah, so I'm gonna just briefly go through again on the introduction.
Well,
so
you don't have to repeat yourself. We heard you, but I just want to be able to see your slides. And so
what happens, like, do you see it right now? The second slide, the introduction slide.
We see the introduction slide in PowerPoint. So I don't, you hit the little button at the bottom, just the normal, I'm not sure that's not working. So I don't know why that wouldn't work. Megan, any ideas, or maybe we could move to someone else, maybe email me your slides, and then we could try that maybe someone else could present while you talk, or I'm not sure how to proceed if we can't your slides. So,
and it also doesn't allow me to share my whole window, which is weird. Like, okay, what happened if I just go from here? And what do you see now?
Still the file. Maybe you can try, maybe we can move on and you can make a PDF or something. We could try to come back to you. I don't have any ideas. I don't know.
Okay.
Why it doesn't work. And email them to me as well, and maybe I could try to flip through them. But for the sake of time, I think I'm sorry to do that to you. I know it's hard to stop in the middle and have to start again, but I think without being able to figure it out, why don't you take those couple of steps and we'll move on to Anais and come back. Yeah, and email me. Don't forget to email me your slides and maybe I can advance them. Hopefully I don't have the problem you're having. Okay, so technical difficulties. We didn't have any yesterday, so we're getting extra maybe today. In the movie panel, we had a lot of challenges too. Okay, so Anais Ostroski is a doctoral student in civil and environmental engineering at the University of Pittsburgh, focusing on food, energy, water nexus. Excited to see her work because some years ago now, worked on a proposal with Vikas and learned a little bit about what he was doing. It's really fascinating. So so we're gonna hear a little bit about her work, but generally Anais is interested in utilizing methods from data science, linear optimization, LCA, and network analysis to uncover connections between food, energy, water, with a particular interest on the consumption side perspective, which I'm really interested in as well, and is not talked about enough. So let us hear from Anais.
Hello, thank you for that introduction. Nice to meet you all. I'm just trying to share my screen.
Okay, hopefully you don't have any problems. No Anais.
Can you see this?
Yeah, looks good.
Okay. All right, so as said, my name is Anais. I'm a PhD student, and today I'm going to talk about consumption-based accounting of environmental impacts of beef supply chains in the United States. So literature has shown that reducing meat consumption is an effective way to reduce environmental impacts. And we know that even though consumers often underestimate the environmental impacts of animal-based products, we also know that in general, people are willing to change or partially change their diets once they are aware of this. There exists a rich body of work on water and nutrient impacts of agriculture and food products, but consumption-based accounting is relatively scarce, and understanding these values from this perspective can be even more helpful to consumers, especially if we improve the granularity of consumption-based footprints and actively link consumption to the often distant places where production happens. With this in mind, our objective is to develop a framework to quantify consumption-based environmental impacts of food in the United States. And we do this by linking production to consumption at the county level through optimization. And we evaluate spatial differences in environmental footprints, namely virtual water and virtual nitrogen. Our work with virtual nitrogen, however, is still ongoing. So I'm going to talk about where we're at and our methodology, but the results I'm going to show you are going to be mostly related to water. So this is the general methodology of our work. We mainly rely on publicly available data sets to construct the supply chain network, and then we incorporate environmental impacts to get an embedded impact network. The objective is to trace impacts from feed to the ranch where the cattle grow, to the feedlot where they eat and gain more weight, to slaughter and consumption. I also wanted to highlight the third photograph in this slide, which shows how massive these feedlot operations are, and they seem to be very impactful. This is the conceptual network. So again, we're tracing feed, cow-calf to cow-calf in background, feedlot, slaughter, and consumption. It's important here to say that consumption is defined as the county of consumption, and we are using average per capita values to estimate that. Unfortunately, we don't have more specific data on retail and restaurant consumption. So these are the two main data sets that we use to trace animal movements. The first one is the feeder cattle sales, which are the cattle that are going from the ranch where they grow towards the feedlot. And then the second one is the cattle on feed sales for slaughter. So they're leaving the feedlot to go to the meat packing plants. The first one was estimated based on all of the USDA cattle data. And the second one, we did have to estimate about 25% of it was missing. We did use machine learning. The cattle, the states that show in gray altogether are less than 1%, and we didn't have enough data to estimate those. So the supply chain network was built in two parts. The first one was to minimize costs of meat packing plants when buying slaughter cattle and when distributing the meat. And then the second one was to minimize costs of the feedlot operations when buying the feeder cattle. There's a third one that we are currently working on that is to more specifically trace where the feed is coming from. And that will be for the nutrient work. So this is the general framework, minimizing costs based on a classic transportation problem, as in operations research. Our constraints ensure that we're respecting the capacity of production, demand, material balance, and load lot, which is the number of animals per truck. Very similarly, the operation framework for the feedlot is a transportation problem with the price of purchase to purchase feeder cattle. And again, capacity and demand constraints. To calculate the water footprint, we adopted the methodology described in Mobacco 2011. The methodology is state-level average water withdrawals and water intensities associated with crop production multiplied by the feed intake. However, rather than calculating the water footprint at the end of the animal's life, like it's normally done, we disaggregate these values to represent the water footprint at the end of each phase. This is an important change because we are tracking and they are not, they do not occur in the same place. For the nitrogen model, we follow IPCC 2019 guidelines at the tier 2 to calculate the reactive nitrogen losses in each and every stage. We are calculating losses through volatilization, runoff, leaching, and nitrous oxide emissions. We currently have those fractions at the subnational level, and we are considering different manure managements in each one of those cattle operations, as well as specific synthetic fertilizer data for each one of the feeds. We are also considering feed that is byproduct from the ethanol industry in this model. So the result was a 3-echelon network between cow-calf, feedlot, slaughter, and consumption counties, and approximately 9.5 million tons of beef were consumed. Again, as I said, we are currently working on improving that network to consider more specific feed counties. This is what the general first link looks like. We see a huge inflow of cattle going towards the southern and northern plains. That's where most of the feedlots are. And this one shows from the feedlot to the slaughterhouse. So those meat packing plants are also very, very close to the feedlot area, with a few exceptions. Note the number of animals produced. The number is huge, and it's approximately 4 companies that own most of these slaughterhouses, and they're responsible for almost 90% of production. And this one is the link from slaughterhouse to consumer, considering transportation, cost minimization. Now we have the correlation between production and consumption. This is a bivariate map showing this correlation. So I would say highlight the East Coast. You see in red and pinkish, it means that it's mostly high consumption and low production. In the East region, excluding the East Coast, you see more of a mix within each state. As we head west, in this blue color, it means that these counties produce a lot and they do not consume that much. And then finally, in the West Coast, the counties seem to be big producers and consumers alike. This is the water footprint for each phase. Each point in this graph represents a state, and you can also see the density distribution of those water footprints. Beef cows have the largest deviation and the largest water footprint requirement, mainly due to their feed requirement and the length of the phase. But feedlot cattle have much higher intensity per day, but the length of the phase is much lower. So this core diagram shows the virtual water flows. It is organized from the highest consumer, starting at the 90-degree mark with California, and then to the smallest consumer. A few links that I would like to highlight is that Texas does receive virtual water from other states, even though it's perfectly capable of producing meat to cover the consumption. The link from Colorado to California in pink is actually larger than from Colorado to Colorado, which means that they're just sourcing a lot of their product to California to meet their large demand. Also notice the number of colors in the incoming links in states like Florida, New York, Pennsylvania, Illinois. Those are highly connected states. They're connected to more than 30 states. And states like Nebraska, Idaho, Montana, South and North Dakota are very important suppliers, but the consumption values are generally low. Finally, we are comparing production-based water footprint versus consumption-based water footprint. You can see that it's a pretty big difference. Since there is so much movement around the country, the water footprint production-based of a given state does not necessarily represent the water footprint of products consumed in that state. If you look at Arizona, for example, they have the largest water footprint in terms of production, but they are sourcing a lot of their product from Texas and Kansas. So the consumption-based water footprint is not too far from the mean. We do see a general pattern that the Western states have larger water footprint than the Eastern states. So a few conclusions is that cattle usually travel to the center of the country because that's where all the feeding and slaughtering operations are. And a small number of key counties and meat packing facilities are responsible for great percentages of beef production. And consumption-based water footprint is dependent on the source and the specific supply chain. I'm very excited to see what we are going to find with our nutrient work. Unfortunately, I don't have results to show now, but I'm excited to talk methods with you. This research was supported by the NSF, and here is my email in case you want to contact me. Thank you so much for your attention.
Hello. I was writing a note to ask you a question. Any questions? Quick question. I have a few. I think I will hold most of them. I'll ask one. Most people are thinking, is the larger footprint on the west due to accounting for those animals actually being hotter and needing to drink more water, or is it more that it's like extracted water, or what do they call it, blue water? Like, is it? How does that work out?
It's mainly due to the production practices in feed production. So how they use much more blue water than the states in the center, in the southern and northern plains.
Okay, yeah, I was curious. Long ago, we were looking at how much more water an animal needs like per degree, and it does escalate pretty quickly. Any other questions from anyone? I do have more, but I think we'll wait until the end because I think they might build. We'll talk about nitrogen. I'm very curious about how you're estimating feed, and that's a huge challenge. And Mikaela and Zia both we've done something, but we could talk about that later.
Yeah, sure. Thank you.
Okay, and yes, so I'm going to ask Mikaela the question, but I'm going to hold it towards the end because I think we'll revisit just how do you think about animal diets in a world where there's like this whole sub-market and it's very hard to know what they're doing. Okay, so let's go back to Zia, who I believe has his technical issues sorted out, and will talk to us about his work again. I'll introduce it again because I think we are ready.
No, it's me. Like I believe you can see it right now.
Okay, great. Okay, good. Yeah, that's.
And I think
see it. That's
you can
great.
see
Okay,
moving,
good.
right?
Yeah.
Okay.
Yep. So I think you can skip this one. I mean,
Yeah, we can skip some of
we all know, right?
stuff. Yeah, and also these. Yeah, I also talked about like footprints.
I mean, you could start here.
Hello, everyone. Sorry about these technical difficulties. Well, I'll jump into like the objectives. So the objectives is basically where I would like to focus here is estimating the NMP embodied in the manufactured food at the national level, and as well as calculating the NMP footprints for all the food manufacturing sectors. So this is basically the flow of the methods. So what happens, like the data from community specific net anthropogenic phosphorus nitrogen input model, or in short like the SNAPNI model data were mapped to the latest BEA 2012 input output sectors, just to create the nutrient intensity vectors, basically by dividing the total economic output of each sector, and this is basically represented by here as R. And also we derive the direct requirement matrix and demand vector from the BEA latest 2012 input output tables. So just to give a perspective on like what kind of demand vector we basically utilized here. So it has like a number of different components, and we basically utilize the personal consumption expenditure, which is representative of purchases of household, and also just to let everyone know that the PCE is about like 70% of the GDP. And when we put together all these data into these equations, and we'll have our sector-wise embodied NMP for the consumer purchases. Well, so the very first graph here we see how crop commodities contributed as fertilizer nitrogen, fixation nitrogen, and NY nitrogen embodied to the total of each sector. And if we just look at the legend, the green shade is basically for fertilizer, and the blue shade is basically for fixations of different agricultural production system. Sector, and NY is basically representing the oxidized form of nitrogen, sort of mostly NOx, and some of the dinitrogen, pentoxide, nitric acid, and other organic soluble nitrogen. So just to give us a sense of the results, it's basically the system-wide results, not like the per unit result. And what we see, the animal except poultry processing has the largest amount of embodied nitrogen, primarily reflecting the food and feed associated with this livestock industry. And also we see bread and bakery sectors as the second largest embodied nitrogen, a finding which has not previously been identified as a major source for embodied nitrogen. And just to have some facts on how bread and bakery sectors work here in the United States. Like United States is the largest consumer of bread and bakery products, and also the largest producer base is here in the United States. And also we see a difference in total embodied fertilizer nitrogen, and bread has more higher embodied nitrogen fertilizer in this sector, and partly due to the inputs from the animal export poultry processing, poultry and egg production, and cheese manufacturing contributed to the embodied fertilizer nitrogen. And obviously the largest share basically comes from grain sector, a flour milling sector, and as well as wet corn milling. And also we see like a higher amount of embodied fixations nitrogen in snack food, partly because like it requires a lot of oils for frying, which basically comes from oilseed industry and oilseed processing industry. And also we see like a part of contribution from other crops farming, where it basically buys peanuts, which has one of the highest fixation rates. Also, we see like higher amount of embodied fertilizer in frozen food, partly because of it purchases from grain farming, flour milling, and etc. So, and also we see the food service sector are contributing higher, and they secured like higher positions than many other sectors here we see. So depending on what we see here, like for the top 5 sectors, it accounts for 32% of the total embodied nitrogen for all 43 sector we considered here. And similarly, for the top 10, it's about 53, and top 20 is basically 82%. And this second figure, it shows the contributions of crop commodities and P diet supplement to the total embodied P for the top 20 sector and out of 43 sector. So again, the green shade is basically for fertilizer, and the red shade is basically P diet supplement used in animal production system. And just if you'd like to see any compare it to the previous nitrogen embodied ranking, so we see like there are differences in ranking, and also we see the poultry and egg production and cheese made to the top 20, partly due to the P diet supplements for the LT and fruit production system and dairy system. And large percentage of P diet supplement is basically due to the P diet supplement used in poultry processing and production system, which is reflected here. And so here for the same for top 5 sector, we see 41% out of total 43 sector, and the top 10 account for 61, and top 20 account for 85 sector out of 43 sector we consider here. So now the most interesting thing of our analysis is nitrogen footprint results, which basically connected this commodity level estimate to the manufactured foods that people actually eat. So here we see the nitrogen footprint values for the top manufacturing sectors. And also what I said, like we wanted to see if our estimates sort of match or fall within the range of the current estimate of consumers' nitrogen footprint only for the food portion, and we see our estimate falls within their range, and the average between, we have a difference for the average values, and partly due to the number of community basically they considered, and we also considered the atmospheric depositions, which the other analysis didn't consider, and also they have like a small amount of recyclable nitrogen. And also they adjusted the food loss, which actually accounts for a very small amount of nitrogen physically embodied in the food waste. So, and also we see like higher amount of embodied nutrients in service sector. So this is the result for the phosphorus footprint. And again, for the difference, we see like we have a close proximity, and the difference can be attributed to, again, between the number of commodities they considered, and obviously the assumptions they used for the P diet supplement. So what they assume that only 5% of the mineral P is used for the animal diet supplement. And also here in this case, they also adjusted it for food waste, which we haven't. And again, it represents a very small amount. And also their estimate of wastewater losses sort of combines these detergent, phosphorus, and as well as phosphorus from human excreta. But we avoided the P from the detergent. And also we see like higher amount of footprint associated with the poultry processing, partly due to his pea diet supplement. And what happens, like poultry have troubles digesting pea in the crops used for the animal feed. So as a result, inorganic pea supplement make up a large percent of poultry processing and poultry production system. So finally, I believe our estimates provides an opportunity for consumers to reflect on how their actions are linked to national nutrient flows, and adding to that, like a staggering amount of food are wasted in the United States in each year, largely at the consumer level. So the NMP estimated for the manufactured food will have a positive impact for food loss reduction, given that there are adequate education and campaign programs. And also this work has relevant for understanding the ongoing sustainability of dietary choice discussion. And our future work will include the other indicators such as GHG emissions, land use for better trade-off analysis. And I would like to acknowledge those organizations and individuals for their contribution and support. And I would like to stop here, and that concludes my presentations. I hope if you have any questions or comments, I'll be happy to answer that at the end of the sessions. And yeah, that's all. Thank you.
Glad we got those technical difficulties figured out. Any quick questions for Zia? There will be definitely questions soon at the end. So please share those if you have any, and we will collect those. Okay. I was just checking the chat. So our next speaker is Kevin Omer from UC Berkeley. He's currently a postdoctoral researcher in environmental engineering at the University of California, Berkeley, where he investigates resource recovery from concentrated waste streams. So that definitely ties into everything that we've talked about so far, because there's a big opportunity there to recover those nutrients, and it may be really important if we're running out of phosphorus, right? Dr. Orner was previously a Peace Corps volunteer in Panama and was awarded a Fulbright research grant to investigate nutrient and energy recovery in Costa Rica. And he will be joining faculty at West Virginia University this fall. Congratulations on that.
All right, good afternoon, everyone. I'm going to share my screen here.
That looks perfect, yep.
Great. Good afternoon, everyone. I'll be talking a little bit about fertilizer demand and potential supply by integrating anaerobic digestion with different nutrient recovery technologies, specifically for the state of California. And this is work conducted at UC Berkeley, as well as collaboration with Sarah Smith and others at the Lawrence Berkeley National Lab. Briefly, I'll be doing introduction, methods, results, and discussion, and then finish with implications and next steps. So here in California, this is nitrogen balance back in 2005. The imports are on the left in blue, and the exports are on the right in red. And you can see that 37% of the nitrogen imports were from synthetic fertilizer. And then looking at the nitrogen exports, you can see a lot of nitrogen is lost in the form of gases, nitrogen going to groundwater, or even food. So there's kind of this leaky balance here. We're bringing in a lot of nitrogen, and also a lot of nitrogen is lost. Some of you may be familiar with anaerobic digesters. It's typically used for carbon treatment. You have organic carbon coming in, you have some carbon leaving in the solids, and you also produce methane, CH4, and carbon dioxide, CO2. But what also goes on during anaerobic digestion is the mineralization of nitrogen and phosphorus. So you have organic nitrogen coming in and leaving in the effluent as ammonium, and then you have organic phosphorus coming in influent, and that's discharged in the liquid effluent as phosphate. So there are many different types of inputs into anaerobic digesters. Of course, there's municipal sewage sludge, but you also see, especially in California and in other states as well, different inputs into anaerobic digestion, such as animal manure, agricultural crop residue, agri-food process residues, and organic municipal solid waste, especially food waste. And this is especially relevant here in California because there are 3 different Senate bills that are motivating this work. One is Senate Bill 1383, which aims to reduce methane emissions from manure landfills, and also Senate Bills 100 and 1260 that deal with renewable energy and agriculture and forestry burning. So there's one study done by Cal Recycle that estimated that new infrastructure was needed to improve digester capacity to meet these organic waste reduction limits, and that capacity would need to jump from 1.2 million tons to 5.1 million tons to meet that Senate Bill 1383 goal, and that's by 2025, so 4 short years from now. That there's a lot of infrastructure that's needed to treat the waste, and then the question is, what are we doing with all the nutrients that are in the outputs from the digesters? So a previous study looked at the market potential that was looking at energy, so looking at anaerobic digestion infrastructure that considered recovery of energy from biogas under different market and policy scenarios. So the goal of this study was to say, okay, we've done the study for energy, what's going on with the nutrients? So how much nitrogen, what's the mass of nitrogen that's coming from these digesters, and what's the mass of phosphorus? And can we recover that nitrogen and phosphorus by integrating nutrient recovery technologies with existing or future anaerobic digestion infrastructure? And then comparing the significance of this mass of recovered nutrients to the regional fertilizer demand that exists currently. So in order to carry out this research, first we looked at the different organic waste streams that became the influent to the anaerobic digester. The digester produced biogas as well as liquid and solid digestate, and then that digestate can be separated into its liquid and solid streams. And then in the model we had different liquid nutrient recovery processes and solid nutrient recovery processes, and the output of those were either liquid fertilizer or solid fertilizer. And that produced quantity of nutrients for fertilizer was then compared to the purchased quantity of nutrients in synthetic fertilizer. So just in a little more detail, there are 5 different organic waste streams that I already mentioned, and these can be categorized as gross, technical, or market. So gross is basically the entire mass that exists of that organic waste stream, and then a subset of gross is technical, and technical is what is cost effective to collect but not currently used in another market. And then a subset of technical is market, and market was the result of a private sector build out model. So what could be profitably built under current cost conditions, and then a range of market and policy drivers. And then going on from there, I was able to research and come up with the concentration of nutrients in each of these organic waste streams. So this was really necessary because they're not all the same. The nutrient concentrations are different for each organic waste stream. And then looking at what's going on with nitrogen and phosphorus during anaerobic digestion, and then what % of the nutrients are going to the liquid and solid streams during separation. And then lastly, looking at the nutrient recovery technologies. And in this case, we looked at technologies such as struvite precipitation, ammonia stripping, distillation, and then composting. This is a very intense literature review. So here are the results. First, for the organic waste streams. So this is the dry mass of organic waste streams in California in 2020. On the x-axis are the different categories of gross, technical, and then a high market scenario and a more conservative low market scenario. And on the y-axis is the mass of the organic waste in gigagrams per day. So you can see that there's definitely a drop off between gross, technical, and then market high, market low. And this is primarily because there's these % contribution of each organic waste stream, and there's these wide variety of differences, like we talked about for transportation of animal manure, for example. So there's differences in feasibility and cost that restricts which organic waste stream would be most profitable. So you can see for gross, the largest contributor is organic municipal solid waste. There's still a lot of animal manure there, but as we get to the market high, market low scenarios, The largest contributor is municipal sewage sludge and also the organic municipal solid waste. And then looking at the end of the model, after going through the process of digestion, separation, and then the nutrient recovery technologies, this was the results of the mass of nutrients in the produced fertilizers. So you can see on the x-axis is phosphorus and nitrogen for a 2020 scenario and a 2050 scenario. On the y-axis is again tons per day of the mass of nutrients. So you can see for 2020, the majority of nutrients comes from municipal sewage sludge, whereas as we move on to 2050, the overall mass is higher, and then these other organic waste streams, such as organic municipal solid waste, even animal manure, become more prevalent for both nitrogen and for phosphorus. And then comparing this produced quantity of nutrients to the purchased quantity of nutrients in synthetic fertilizer, we brought it through the model of, again, digestion, separation, nutrient recovery. We've got these produced products such as compost, struvite, liquid fertilizer, and the results of our model indicated that about 2/3 of the phosphorus ended up in the form of struvite, and about 50% of nitrogen was in the form of struvite, and over 1/3 was found in liquid fertilizer. But there's still a lot more work to be done as far as market development for these fertilizers. So if this is done at a wastewater treatment plant, or if this is done at a farm, there's a lot of work to be done to train the utilities or to train the farmers to how to market their fertilizer, and then again, who's going to buy that fertilizer. And then the results of our model said that in this market scenario, we could offset about 29% of phosphorus found in synthetic fertilizer and 12% of nitrogen found in synthetic fertilizer. So they're definitely not fully replacing the nutrients found in synthetic fertilizer, but it does make a sizable dent. So we can look at all these different organic waste streams, not just municipal sewage sludge, to try to close these nutrient cycles. And then for implications and next steps, there continues to be a need for innovation to lower the impact, both environmentally and economically, of these technologies. If the study was done in other states, the mass and location are going to be different for these organic waste streams. It's going to be different in California than in other states. But the results from this study can inform upcoming organic waste policies that might be considered in other states. And then again, we need to do these pilot and full-scale studies when we mix these different organic waste streams for co-digestion and looking at different nutrient recovery technologies to see how this plays out at full scale in the field. Looking at next steps, I'm currently working with Sarah Smith, who's on the call here today, to look at the environmental and economic costs. So we've looked at the mass of the nutrients. We also want to know environmental impacts. Are some technologies, treatment trains better than others? And also, what are the economic costs? That's going to be a major driver for whether this gets implemented or not. And then looking at trade-offs on energy and water quality impacts. And then lastly, if California were to implement all these digesters and nutrient recovery technologies, where would they be located? So I'll be working with Sarah Smith as well to look at a spatial optimization to where exactly it'd be most profitable to do these digesters and nutrient recovery technologies in California. So with that, I'd like to thank you for your attention.
Great. So exciting. California is really driving a lot of this biogas market with anaerobic digestion. It's really exciting. Any questions from the audience? A quick one. Anybody? We do have some questions for the end. I'm wondering, can you just, what drives the increases in 2050? Is that just population expectations?
Population increase primarily, and then perhaps these market and policy drivers will be more favorable for energy production.
Yeah, and even it seems like a lot more manure, or a lot more, it's hard to tell if it was a linear increase for that black piece, and I was just wondering if California is expecting to grow more beef in their water scarce environment or not.
It's primarily due to the price for bioenergy, and even if that increased a little bit, it's going to make it from not profitable to profitable to manage the organic waste streams such as animal manure.
Okay, thank you. Okay, well, there might be another question for you in a few moments. Hopefully we can recover still a bit of this discussion time after our last presentation, which is Dr. Velapil, Femina Velapil, is a postdoctoral researcher here at Penn State in the Department of Civil and Environmental Engineering. She earned a PhD from Purdue in water resources engineering. She's an eco-hydrologist, environmental protection enthusiast, and advocate for sustainable development. And she's going to talk to us today about a novel approach to intercepting nutrients or recovering nutrients out of particularly dairy farm manure with duckweed. So another exciting opportunity. Sure we can.
Thank you, Chris. Do you see my screen properly?
Okay, looks good and sharing correctly. Great.
Is it good?
Mm-hmm.
Yeah, okay. So, hi, like Chris said, I'm a postdoctoral scholar at Penn State University, and today I'm going to talk about economic and life cycle impacts of how we can promote a circular nitrogen bioeconomy in dairy farms, specifically looking at how these small floating species called duckweed can help us to recover some of the nutrients in these farms and enable us to produce some of the protein-rich feed required for the dairy cows. Before I go into the talk, I'd like to acknowledge the funding institutes and also the authors on this work, Ben Roman and Rachel Brennan. So we all keep hearing about how the global milk production and global milk consumption is increasing at a high rate. The figure here basically just shows that dairy cows in particular need more protein, almost 30% more protein in their diets compared to the beef cattle. So we are at a point where we need to start thinking about alternative protein feeds for these dairy cows and also looking more into sustainable manure management practices. So the earlier presentations in the session kind of touched upon how we really need to think about efficient manure management. So the work here is basically connecting these two components of coming up with some alternative protein feeds and also sustainably managing the manure in dairy farms. So let's look at how conventional dairy farm practices work. So specifically for this study, we are looking at the protein feed that is used on sites in these dairy farms. So most of the cases, most of their dairy farms kind of import their feed, especially the protein-rich feed, which is soybean. A lot of the farms import that from offsite, which comes with a lot of increased greenhouse gas emissions and land use change impacts. Of course, there are farms which would produce their own soybean. We're also looking into that scenario in this work. In terms of manure management, a lot of the farms either store them or trade it to other farms or simply apply them to their crop fields, which again comes with a lot of water quality issues through runoff and leaching. So in our study here, we're basically trying to promote a circular bioeconomy approach in these dairy farms. So what I just talked about, the conventional practices, is what you see here. The manure is coming from the dairy cows and it's applied to the fields. And if the farmer has a crop field, and then the soybean produced in these farms are fed back to the cows. But again, it comes with the greenhouse gas emissions and nutrient runoff and all those harmful environmental impacts. So what we are proposing is to use this manure to basically grow plants or species like duckweed, and then use that duckweed to feed it back to the cows. So we are eliminating the nutrient runoff issue when we are looking at the circular bioeconomy approach. And then with localized protein feed production and this dairy wastewater treatment, we are looking at a more sustainable, environmentally sustainable approach as well. We are also looking at the economic impacts of this system. So what are these duckweeds? They're basically very small floating plants with a very high growth rate, doubles almost every 2 to 4 days. It has almost 45% protein by mass, depending on the species. can be easily harvested compared to other species like algae, and it grows under a wide range of pH and temperature. So in terms of sustainability, it can be used as a biomass feedstock, as an animal feed, human food. There are actually countries around the world which uses duckweed in their actual diet. And it can also be used as fertilizer substitute in farms. So the study objective is basically to conduct a techno-economic analysis and life cycle assessment of 3 main scenarios. So the first scenario is we're feeding the cows their conventional diet, in which 10% of their daily ration consists of soybean that is imported from offsite. So that's our baseline condition with imported soybean. The second scenario is where we replace this 10% of the ration with soybean that is grown on site and which is fertilized with partially treated manure. And the third is where we introduce duckweed to replace the soybean. So the duckweed is grown on this partially treated manure. And we are also looking at 3 different drying techniques for this duckweed scenario. So some of the selected inputs and assumptions for the LCA, we used SIMAPRO for our LCA functional unit was 1 animal unit, which is equivalent to 1,000 pound cow. Time scale, we started with an annual scale for both LCA and TEA. For the economic analysis, we also looked at a long-term analysis of how economical the system is. For LCA, this is a work in progress, so we're still looking at the life cycle assessment for a 20-year time span. This is just the dairy cow diet that we use. We got this from a local dairy farm. So if you particularly look at soybeans, this is what we are trying to replace with duckweed in the cow diet. So just recapping the 3 scenarios, we feed the cow with the conventional diet. The manure is stored on site. In the second scenario, it's spread on soybean fields, which is used as feed back to the cows. And the third scenario, we use them to grow duckweed, which is also fed to the cow. The 3 drying techniques we use for the duckweed, one is the conventional oven. Second one is a hybrid solar dryer, which is kind of like a greenhouse, but it also has solar panels. So it would generate electricity to basically dry the duckweed. And the third is a natural sun drying technique, but it has some protection from the rain. So we are using a tunnel sun dryer for that technique. In terms of impacts, we looked at land use change impact, climate change impact, and resources. So coming to some of the results, this is the techno-economic analysis results. So the graph here is showing cost over 20 years per animal unit. So you have to keep in mind that if we're looking at a farm, maybe for 100 animal unit, this would be more exaggerated. So this is just per animal unit. If we look just at the first year cost for these scenarios, you can see here the duckweed scenarios come with high cost in the initial year, and that's mainly because of the pond installation and the installation of the drying equipment for these scenarios. But over 20 years, you can clearly see that the duckweed scenario is cheaper compared to the soybean scenario, with sun drying being the cheapest option of all. Coming to some of the life cycle assessment results. So this is kilogram carbon dioxide equivalent per animal unit in a year. Soybean import scenario comes with a high climate change impact, negative climate change impact. The duckweed scenario, the oven drying and the sun drying comes with a lower impact compared to the solar drying, and that's mainly because of the initial resources that's needed for installing this hybrid solar dryer. Same thing if we go to the resource in terms of how much non-renewable energy is used for these scenarios. Again, this solar dryer scenario, you can see high resource impact because of that initial year construction of drying house. And like I said, this is a work in progress. So we are hoping that when we look at the impact over 20 years, we will hopefully see this reduce substantially compared to the soybean scenario. You can see here the annual energy savings that we get from the natural sun drying or the solar drying scenario compared to oven drying. So this gets added for each year if we are looking at a longer time span. In terms of land occupation, again, soybean imported scenario has a high impact because you're looking at land that's needed for growing these feed and then transporting and all that stuff. With the year, if you just look at the yearly land occupation needed for cultivation, you can see here that soybean actually requires more area compared to duckweed for an equivalent production of protein for the cows. So again, this is just for an year. So if you're looking at a longer time span, this would just add up for each year. So right now, for just 1 year, the soybean and duckweed scenarios look similar. But overall, the natural drying scenario for the duckweed is the one with the lowest overall impact. In conclusion, we hope to take the study forward because we really feel that duckweeds offer a sustainable option to produce protein and also as fertilizer substitute. We haven't touched upon that in the study yet, but that's something we are exploring to use them as fertilizer substitute in these farms. We could see that importing soybean actually comes with a high amount of climate change and land use change impact. And in terms of economical benefits, although if high in initial investment, we feel that duckweed cultivation will definitely be economical over a period of 20 years. In terms of work forward, we would like to refine the LCA more with additional data from our local dairy farm and assess it for a longer time span to see how that changes between an annual time scale and a longer time scale. We are hoping to incorporate vertical farming scenario because that's something that would mitigate land use change impact for these duckweeds. And we're also considering different levels of daily ration replacement, just keeping in mind adequate cow nutrient consumption too. So that's it. Thank you. I'll be happy to take any questions or suggestions. Like I said, we would really appreciate any additional suggestion to improve this work. So yeah, thank you.
Nice. I think the rest of the panel will be brought up, and there's some questions in the chat. Sorry, we don't have as much time as we had hoped. Any questions for Femina about the duckweed system? I'll let people think about that for a moment. But we have a couple questions for Kevin. Excellent presentation, Olivia says. What is the current market for recycled nutrients from waste sources? Those 2020 data reflect the current implementation. Do those, 2020 data reflect the current implementation or the potential % of nutrient demand that could be supplied by waste recycling?
All right. Yeah, the current market is definitely the next question to answer here. Our lab group is in partnership with the East Bay Municipal Utility District, and they just recently had a market study done that was looking at what are the different fertilizer products and who's going to purchase them and kind of like what's the radius. And EB Mud is a larger utility, serves a lot of people. They had the money to spend and determine, and get in contact with real people and real organizations who would purchase it. But, that might be more difficult for smaller utilities that may not have the money to fund a market study like that. So that's the purpose of this next study, is to really get into the economics and the markets and see if we can make that more clear, because that's going to be a needed path forward, because the path forward to make this make economic sense is to either sell the fertilizer product or to show that, the environmental impacts will make you not spend money in other places. But yeah, that's the next step of the study.
Such a huge challenge. There's a little bit of movement over here on the East Coast around the Chesapeake Bay to maybe have a nutrient trading market, but it seems to always doesn't quite get off the ground. But yeah, it would be nice. but that would be another option, perhaps. Another question for you, which is kind of related, I think, just in terms of the form of the nutrients that you have and all this kind of thing. But what are the current most common nutrient recovery technologies? You mentioned the need for future innovation for lower impact nutrient recovery technology. What are the main challenges and the impact that current solutions that need to be optimized?
Yeah, so in our research, we looked at things that have been implemented at the pilot or the full scale, and we came up with struvite, which is mostly for phosphorus recovery, and then ammonia stripping thermal distillation, which is primarily for nitrogen recovery, and then composting for the solids, but compost may not always be a direct replacement for existing synthetic fertilizers, so that one may not be an apples to apples comparison. There are other technologies that are kind of a little bit further behind, not, maybe perhaps moving from the lab scale to the pilot scales. There's technologies like ion exchange, for example. I know microbial fuel cells are trying to scale up. And I also know that in Europe, there's a BUNA process that's, I think, partial nitrification followed by a distillation step. So there's a lot of technology development, but that needs to be coupled with these economic, environmental, market assessments. So it's definitely a lot of players that need to work together, and it's not just players in engineering.
Yeah. Do you think if natural gas prices went up, some of this technology would be more feasible?
Yeah, if you're coupling organic waste with, biogas production, if other energy sources are more expensive, that may drive more market towards anaerobic digestion.
Yeah, like those. It's so fascinating to think that there would be that distillation or the I forget what you just said, and I've heard of it before. But the ability to actually get ammonia out of a digester is really, really cool. But it's probably hard to compete with cheap natural gas to make it how we usually do, right?
Yes.
Such a challenge. So frustrating. I'll leave it there. I get frustrated because I'm kind of like, oh, we have all these things that we could do, but the money doesn't work out, and it feels kind of like, well, someone's got to give sometime. Okay, another question. This is for Famina from Peter. Regarding the duckweed, the question is, it seemed it was used to replace only a small fraction of the feed for cows. Could it replace a larger fraction of their feed, for example, corn, or is there something limiting that?
So the reason we decided to replace soybean is because the protein content in the soybean is very similar to that of duckweed. Soybean is the one that's mostly used as a protein supplement for cows. So that's the reason we used. And regarding the percentage we substituted, we talked to the dairy farmers in the area, and they didn't want to go anything about, say, 10 to 15% because they were worried about nutrient consumption. So we are also working with the animal science people here to really see how feeding the duckweed would mess up with the nutrient consumption in the cows. So that's something we are still working on, and it's something we would really need to work with the farmers here to see how much really they want to introduce a new feed into their diet.
Yeah, it's a tough thing to know, and yeah, the animal science people are putting the duckweed into little fake cow stomachs in their labs, probably as I speak. So hopefully we'll figure out how to do that. Another question for Kevin from Peter. You shared the statewide flows of N, and this could maybe be for all of us here because I think everyone is familiar with like the USDA data. It seems like we're all kind of using this county level data, but you shared statewide flows of nitrogen and maybe phosphorus for California. Where does this data come from? Is it available for other states?
Yeah, so that data was put together on a project primarily led by University of California at Davis, and it was just for nitrogen, and it was just for California. And that was a very intense effort of tracking down, I'm sure county by county data for the entire state. So that report is publicly available, but I know California often is different than many other states as far as like putting together these really thorough, informative, statewide studies and collecting data. So I'll leave it to the other panelists if they know of other resources for other states, for example, for nitrogen or phosphorus.
Anybody else want to comment about the challenges of data, especially at a spatial resolution? It's hard. I think everybody, well, Anais, I think you're using county data. I know Zia and Mikaela are using county data. And then typically, like, thinking about the waste flows is sort of, at least what I've seen, is usually like an endeavor to kind of trace and see like where are all these wastewater plants and how many people live in these places. Challenging. One more question for Femina from Zia. Do you have a plan for including the impact of nutrients in your analysis?
So we haven't thought about that. That's a very good question. Right now, we were just looking at the impacts in terms of, environmental impacts in terms of greenhouse gas emissions and climate change and land use change. But we have other projects that we're doing in the lab where we're specifically looking at nutrient, how we can reduce the nutrients by using these duckweeds to replace the soybean. Like I said in the presentation, where we can really reduce the nutrient runoff from the fields by using these duckweeds. We haven't used that in the LCA yet, but we have other studies where we are looking, at a larger scale, how we are able to reduce the nutrient runoff by producing duckweed to replace soybeans.
Yeah, so remember that right now, basically the manure is stored 6 months to 12 months and then spread, and sometimes it's spread in the winter because they got to get it out. And so the hope is that there'll be this interception. There's also a good text chat in here explaining how machine learning was applied. 659. I'm tempted to ask you, though, to quickly explain. Could you just summarize how you use machine learning? Because I think a lot of us have the trouble of missing data, especially in counties where there's like one huge farm and they just keep all that data because you can tell who it is. So give us the short version, would you mind?
Yeah, sure.
Thank you.
It was a pretty big challenge. What we did was to use a lot of different data to see which ones were not missing. With cattle data specifically, so the USDA has a few different categories that, for cattle, and then you can kind of use those to estimate which ones are not in that category. But yeah, we did use classification to see which states have the similar production practices, and then regression with different methodologies. We've tried many different models to try to find those missing values based on number of operations or number of cattle in that county, etc.
Mm-hmm. Cool. We might be reaching out to you for a little bit more detail, and also I'll recommend that maybe you and I'm going to put a recent paper from Mikaela in the chat, if I can find it. My main chat is missing. That talks about how we allocated, or Mikaela allocated, corn fertilizer to the ethanol and also the distillers' grains, and then thought about that through the diets. And I'm sorry we didn't get to talk about diets because that is a really tough thing, and I wanted to get into that a little bit, but we are out of time, so we will just have to catch up with each other either in this conference or another time. Kevin shared a couple links here too, so make sure you check those out. Okay, well, thank you for your work on nutrients. It's important that we keep talking about nutrients. It's not just about carbon and money. And it's a big challenge, and it's exciting to try to figure out, because lots of new opportunities. Anaerobic digestion is really coming through, and really excited I'm working on this project with Femina. We met just a couple weeks ago, so some of this work is new to me, but on this duckweed project for the next few years, so hopefully we'll be able to share some of that results and have good work from the animal scientists that we can feed these animals with more duckweed. Well, thank you very much, and nice to see your cat. I wish mine was here so they could say hi to each other, but that's one of the good things about all this time online is that we get to see each other's pets. I give extra credit if I can see a cute puppy during class or something, help us all out. Okay.
Right.
Well, thanks a lot.
Thank you so much.
Thank you.
All right. I love how this app screenshots the most unforgiving photos of all of us.